Hi everyone! We are in Lesson 3, Magnetic Circuits and Electrical Machines. In this video, we are going to explain the first two sections of this lesson, which are the Introduction and 3.2, the section of Magnetic Circuits. So first of all, in the Introduction, we have to define the concept of an electrical machine. An electrical machine is a device whose purpose is to produce or use electricity, mainly in the industry, but also in the transmission and distribution of electrical energy. So, an electrical machine must be able to transform electrical energy into mechanical energy, or electrical energy into a different form of electrical energy. In all these machines, we are going to have an input energy and an output energy. So we introduce an input energy into the electrical machine and it gives an output energy. The type of energy that we have in the input and in the output, we can distinguish among different electrical machines. So, for example, a transformer is an electrical machine whose input is an electrical energy and whose output is another electrical energy. A typical use for transformers is to change the voltage, for example, from medium to high voltage after the generation of electrical energy and for its transmission at high voltage, minimizing then the electrical losses, or, for example, from medium voltage to low voltage for the distribution of electrical energy and the consumption of electrical energy at consumption points. The transformer is a static electrical machine because this machine does not have moving parts. Here, on the other hand, we have the motor. So, in a motor, we introduce electrical energy and we obtain mechanical energy, that is motion, okay? So the motor, as it has moving parts, it's going to be a dynamic electrical machine. We also have the generator, in which we introduce mechanical energy and we obtain electrical energy. For example, generators are essential components in power plants because we introduce mechanical energy, any kind of mechanical energy, for example, through a turbine, a gas turbine or a steam turbine, and then that motion generates electrical energy into a generator, okay? And this is another example of a dynamic electrical machine. So, here in section 3.2, we are going to talk about magnetic circuits. Magnetic circuits are very important because they are present in all electrical machines. For example, when we have transformers, we are going to have magnetic circuits inside these transformers, and they are essential for the functioning of those power transformers. Its properties. So when we have a magnetic circuit, the magnitude that represents its magnetic properties is called reluctance, whose units are henries up to -1. So the formula for the reluctance is that, where L is the length of the element which conducts the magnetic flux, so that is the length of the element through which the magnetic flux is flowing, and is expressed in meters. S is the cross-section of the element which is conducting the magnetic flux, and the units are square meters. And this is the permeability of the material. The permeability of the material is frequently expressed as the product of the permeability of the vacuum, which is 4 pi multiplied by 10 up to -7 henries divided by meter, that is the permeability of the vacuum, and the relative permeability is a dimensionless magnitude which depends on the particular material that we are considering and that we have in the magnetic circuit. The magnetic induction, B, whose units are Teslas, is the magnetic flux divided by the cross-section. So, phi is the magnetic flux whose units are Webers, and S is the cross-section of the element which conducts the magnetic flux in square meters. So Webers divided by square meters gives Teslas. The magnetic field strength, H, is the magnetic induction divided by the permeability of the material that we have in the magnetic path. And the units of the magnetic field strength are Teslas per meter divided by Henries. Another equivalent expression for the magnetic field strength is the magnetic difference in potential, whose units are ampere turns divided by the length of the magnetic path, which is the element conducting the magnetic flux. When we have a magnetic circuit, we must distinguish between the circuits which are supplied in alternate current and the circuits which are supplied in direct current. So, in this example, we have a magnetic circuit which is supplied in alternate current. That means that the voltage is a sinusoidal wave that varies over time. Here, the wave has been expressed depending on the sign of the angular velocity and the time, okay? So if we introduce here a sinusoidal voltage, obviously the current is going to be also sinusoidal, a sinusoidal function that depends on time. So the Faraday's law gives a relationship between the voltage that we supply here to the magnetic circuit and the magnetic flux which is going to flow here in the circuit. And the formula is this one. The sinusoidal voltage is going to be equal to minus N, which is the number of turns that we have here in this coil, multiplied by the differential of the magnetic flux over time. So here, if you introduce the formula for the voltage, and you separate variables, you have here differential of time divided, you can take that to the other side of the equation, and you integrate both sides of the equation, you are going to have this formula for the magnetic flux. So if you introduce here the voltage, you will get to this formula for the magnetic flux. So if the voltage depended on the sign of the angular velocity and the time, there the magnetic flux will depend on the cosine, because if we integrate the sign of a function, we will get the cosine of a function, okay? Well, you can try to solve this integral, but we are going to do so in example number 2. So here, when you have the expression for a magnetic flux, you have square root of 2 phi and the cosine of this. Well, here phi is going to be this, okay? The effective value of the voltage divided by the number of turns and the angular velocity. So that is what you are going to have here instead of phi. So if we have the expression for the voltage, as you have seen, we can obtain the time expression, the instantaneous expression for the magnetic flux. And if we know the magnetic flux, and we also know the reluctance, then by multiplying the magnetic flux by the reluctance, we can have the electromotive force. The electromotive force is related with the current and the number of turns. So the current is going to be the electromotive force divided by the number of turns. So in this slide, what you have is, when the magnetic circuit is supplied in AC, the steps that you need to follow to solve the problem is, first, you calculate the magnetic flux. Second, you calculate the electromotive force. And finally, you can calculate the current that is flowing here in this electrical system, okay? On the other hand, when the magnetic circuit is supplied in DC, what you have is that the voltage does not depend on time. so the voltage is constant. And then the current is also going to be constant, and the current does not depend on time. So what you need to do then is, first, the resistance of this electrical circuit here could be obtained as the product of the resistivity of the circuit, its length, and divided by the cross-section. If you have the resistance of the circuit, then this current here, by applying the Ohm's law, you can have that the current is the voltage divided by the resistance. So if there you introduce this, resistivity, length, and cross-section, you will get to this expression. The current is the product of the voltage and the cross-section divided by the resistivity by the length of the circuit. Then, the electromotive force is going to be the number of turns multiplied by the current. So here, as you add the current, you can introduce the current here. And finally, the magnetic flux is going to be the electromotive force divided by the reluctance, or the number of turns multiplied by the current and divided by the reluctance. So as you have seen, when we are in a DC current, the first step is to calculate the current, the second one is to calculate the electromotive force, and the last one will be to calculate the magnetic flux. Now that we have seen this, we can solve examples 1 and 2. In example 1, you have to solve a magnetic circuit which is supplied in DC because the voltage does not depend on time. And you have to consider two different materials of which the magnetic core is made, so wood and iron. In example 2, you have to repeat the same exercise, but now the voltage is a sinusoidal wave that depends on time.
Hi everyone! In this video we are solving example 1 of lesson 3. In example 1 of lesson 3 you have a magnetic circuit where you have a coil connected to this circuit here, and you need to calculate the current flowing through the circuit and the magnetic flux which is going to flow through the coil, okay? So we have that the voltage is a constant one. It's a DC voltage which is applied here in this generator, okay? We have the resistance here in this circuit, in this electrical circuit of 10 ohms. And we have that the number of turns is 1000, and in question A we need to consider that the magnetic core is made of wood whose relative permeability is 1. So the first thing that we need to calculate is the current, and we are going to do so by applying the Ohm's law. So we are going to divide the voltage divided by the resistance, okay? So here the voltage is constant. It does not depend on time. It does not vary over time. And the resistance is 10 ohms. So your current is going to be 1 amp, which is flowing here, and it's constant over time. So when we try to calculate the magnetic flux here is going to be constant, and it is not going to depend on time. So there you are going to have the electromotive force divided by the reluctance, that is the number of turns multiplied by the current and divided by the reluctance. Now then we need to obtain the magnitude of the reluctance. The reluctance is going to be the length of the element which is conducting the magnetic flux, average length of that element, divided by the permittivity and the cross-section of the element. So first we need to obtain the average length of the path which is conducting the magnetic flux. That average length is this one here, okay? So as you can see, you have the average longitude, this circumference here, okay? So to do so, you have to do the average of longitude of the external circumference here, which is 2 pi, and the external radius, plus the longitude of this internal circumference, which is 2 pi, and the internal radius, and divided by 2. As 2 is here in the three terms, you can divide by 2. You can multiply pi by the sum of the external plus the internal radius. So it is pi. The external radius is 15 centimeters, so 0.15 meters, plus the internal radius is 0.1, which gives an approximate value of 0.785 meters. That is the average length of the path which is carrying the magnetic flux. So there you go here and you can obtain the reluctance. The reluctance is that length divided by the permeability, which is the relative permeability multiplied by the permeability of the vacuum. So that is 1 multiplied by 4 pi 10 to minus 7 henries divided by meters. So here you introduce, and you need to multiply by the cross-section. When we say cross-section here, that is the cross-section that we have in the statement of the problem, that is 19.6 square centimeters. So as you need to change the units, you need to use this conversion factor here. Well, if you do so, you are going to obtain a reluctance, which is this one, in henries minus 1. So if you go back here, the number of turns is 1000, the current is 1, and the reluctance is this one. So you will obtain a magnetic flux, which is approximately this in Webers. So here you have the magnetic flux in question A. In question B, you have to solve the same example, but now the magnetic core is made of iron, whose relative permeability is 7,000. So there, you need to obtain the current and the magnetic flux. The current is going to be exactly the same as in the first example, because it does not depend on the material in the situation. It is the voltage divided by the resistance. So the current is 1 amp. So now we need to obtain the magnetic flux. As in the previous case, the magnetic flux is going to be the number of turns multiplied by the current and divided by the reluctance. So we need to obtain the reluctance with the new material that we have. The reluctance was the average length of the path for the magnetic flux, which is the same as before, divided by the product of the permeability and the cross-section. The permeability now is the relative permeability multiplied by the permeability of the vacuum. So that is 7,000 multiplied by 4 pi 10 minus 7 henries divided by meter. You can introduce this. And you need to introduce the cross-section. Remember to change the units from square centimeters to square meters. If you do so, the reluctance that you obtain is this one, which as you can see is considerably lower than the reluctance that we obtained when the magnetic core was made of wood. Now we have a lower value. Here the number of turns is 1000, the current is 1, and the reluctance is the previous one that we have just calculated, which gives an approximate magnetic flux of 2.186 10 minus 2 Webers. And here, as you can see, the magnetic flux is much higher when the magnetic core is made of iron, which is a conductive material, than in the case when the magnetic core was made of wood, which is a non-conductive material. In example 2 of lesson 3, we need to solve the same magnetic circuit with the same characteristics, but now the voltage is in AC. In contrast to example 1, in which we had a DC voltage, that is a direct current system, Here we have a voltage in AC, an alternate current system. That means that the voltage is a sinusoidal wave that varies over time. So we are going to see that there are some differences in the resolution process and in the results, depending on if we are in an AC or DC system. In this example, they also ask the current here in this circuit, in this electric circuit, and the magnetic flux in this magnetic circuit. So in this situation, we need to start by calculating the magnetic flux first. You have in the notes that the sinusoidal wave of the voltage is going to be the same as minus the number of turns divided by the differential of the magnetic flux over time. Here you have a differential expression, so you should separate the variables here. Here, in order to integrate this side of the equation, you need to introduce the expression of the alternate voltage. So here you have the voltage that varies over time, which depends on the cosine of this angle, okay? And in the other side you can extract n from the integral because it is a constant, the number of terms, so minus 1000, and you have the integral of the differential of the magnetic flux. You can extract this in this integral because it is constant, and you are going to have this integral here, and in the other side of the equation, the integral of the differential of magnetic flux is directly the magnetic flux. You need to have here in the integral 100 pi, okay, because it is what you have in the function, in the argument of the cosine. So here you need to divide by 100 pi. So if you simplify here, you are going to have square root of 2 divided by 10 pi, and this integral gives the sine of 100 pi times 100 pi multiplied by the time, and here minus 1000 and the magnetic flux. So at the end, the magnetic flux now, it is not constant anymore. It depends on time. And here you will have, so this is the expression for the magnetic flux. If you remember in the previous example, in example 1, you had that for calculating the magnetic flux, you need to use the reluctance, and in the reluctance you have the permeability of a particular material. So the magnetic flux was different depending on the material that you have in the magnetic core. On the other hand, in this example, example 2, as you can see, the magnetic flux does not depend on the material, okay? Here we don't have any parameter that depends on the material, but it is variable in time. Now that we have the magnetic flux, which is the same when we have wood or iron in the core of the magnetic circuit, then you need to obtain the current, okay? So for obtaining the current, in case A, you are going to have the magnetic core made of wood, whose relative permeability was equal to 1. So in this situation, the electromotive force will be the magnetic flux multiplied by the reluctance, and the current that now is going to depend on time will be the electromotive force divided by the number of turns. So if you go back to example 1, the reluctance in the case of the magnetic core made of wood was this one. And you need to multiply that by the magnetic flux, which follows this sinusoidal wave. So then, as the current is the electromotive force divided by the number of turns, you need to divide that electromotive force by the number of turns, which was 1000, okay? So the current now would be approximately this one. So that is the current when the magnetic core is made of wood, expressed in amps. When the magnetic coil is made of iron, then the electromotive force is the same magnetic flux, but multiplied by another different reluctance. We have the reluctance from example 1. So the product of both will be this one. So that is the electromotive force. Now that you have the electromotive force, the current would be the electromotive force divided by the number of turns, so divided by 1000. So that is this current expressed in amps. As you can see, when the core is made of iron, you are going to have a smaller current flowing here in the electric circuit, and the magnetic flux here will be the same as when the core is made of wood.